Hi, I'm Allie Hayes, and this is my final project for Black Hat Go named Cipher Spider. For my final project, I decided to code encryption and decryption functions for common ciphers in Go. The first thing I needed was a way to implement generic substitution ciphers. I named these functions subencode and subdecode. Subencode and subdecode are the basis for almost every other cipher function I've written. They take a message, a key in the form of a map, and a bool named fill. They return either ciphertext or plaintext respectively. Fill determines what will be added to the generated text when a character that isn't mapped is encountered. If fill is true, the missing character is added as is. If fill is false, a question mark is added. On their own, results generated with fill being true can be hard to understand, as it isn't clear which values have been changed. However, results generated with fill being false can get rid of valuable information, such as which missing characters are the same. These functions can be used with user-generated maps for custom substitution ciphers, but they are also used elsewhere in my code with pre-made maps to implement common substitution ciphers, such as the Cipher cipher. Users can easily generate their own maps with the included quick map function, which takes a 26-character ciphertext alphabet and maps it to the plaintext alphabet, including upper and lower case. It returns that map. The Cipher cipher was the first popular cipher I tackled. It works by shifting the alphabet by some number. So for example, a shift of 3 would encode A as D, B as E, and so on. As such, it is very easy to crack, as there are only 25 possible shifts, 26 if you include 0, which basically just maps the alphabet back onto itself. Nonetheless, this is a very popular cipher, and this code is a valuable building block for other ciphers that I've worked on. Rot 13 is a special case of the Cipher cipher in which the shift value is 13. One interesting trait of Rot 13 is that encoding and decoding can be done with the same function. Another common cipher is the @bash cipher, in which the alphabet is mapped onto a backwards alphabet. Much like Rot 13, encoding and decoding can be done with the same function. Letter number and number letter are exactly what they sound like. Each letter is mapped to its place in the alphabet. These functions work differently from all of my other ciphers, as non-letter elements and capitalization are not preserved. Letter number was first created as a utility function for my next cipher, Visionaire, taking only one rune and returning only one integer. But given that it's a fairly popular cipher, I decided to make a decoding function and change them to work with strings and arrays. I should note that my version of this cipher is 0-indexed, so A equals 0 and Z equals 25. Whereas some other versions are 1-indexed, so A equals 1 and Z equals 26. So far, all of the ciphers I've shown have been monoalphabetic, so if A equals Z once, A will equal Z every time. As such, they have been pretty trivial to crack. The last two ciphers I've coded are polyalphabetic, so A may equal Z in one place and L in another. This greatly increases security. The Visionaire cipher is the most complicated one I have implemented. It takes a key and repeats it enough to match every letter in the message with a letter in the key. These letters as 0-index places in the alphabet are then used as shift values, and each letter is encoded separately with the Cipher cipher. For example, using cake as the key, the first letter would be shifted by 2, the second letter would be shifted by 0, changing nothing, the third letter would be shifted by 10, the fourth letter would be shifted by 4, the fifth letter would be shifted by 2 again, and so on. The last cipher I coded was the running key cipher. This is basically the same as the Visionaire cipher, but with the requirement that the key is at least as long as the message so it doesn't repeat. As such, this function takes a file name rather than a key, and generates a key from the given file. One interesting fact about running key ciphers is that when used with a randomly generated one-time pad as the key, they are nearly impossible to crack. Thank you for watching, and feel free to leave any questions in the comments below. A link to the GitHub repo containing this code will be in the description.